Okay. So can you tell me, can you think on it? If we increase the mask size, what is its effect on filtered image by applying, say, standard averaging filter in spatial domain? So basically, when we increase mask size, it means we are increasing local neighborhood size. And when we increase local neighborhood size, we are actually taking average over greater area. Okay. So that's why when we increase mask size as shown here in this slide, say we switch from 8 neighborhood to 24 neighborhood to 48 neighborhood. That is, here mask size is 3 by 3, then 5 by 5, then 7 by 7. So when we go for greater mask size, we are taking average over greater area, and that's why it causes more amount of blurring. Okay. So this is one effect of increasing mask size. As we go on increasing mask size, more and more blurring takes place. Okay, so as you look here, the same is indicated here. This very first image is original image. Then these next 5 images are result of filtering this original image by increasing mask size. Here mask size used is 3 by 3, then 5 by 5, then 9 by 9, then 15 by 15. And here mask size is very large, which is 35 by 35. So if you compare your result by mask size 3 by 3, that with mask size 35 by 35, it is very clear that more amount of blurring takes place. Now in this original image, there are, if you observe, there are squares on the top. This very first square size is 3 by 3 pixel. Then here this one is by of size 5 by 5, and slowly the square size is increased. This last two square is of size 55 by 55 pixels. Okay. So if you compare these results of filtered images by various mask sizes, just look at this third image, that is second image from second row. Okay. Here first 3 squares from original image, those are blurred to a very great extent because this image is filtered by using a mask size 9 by 9. So all the squares from original image having mask size, having square size less than that, those are blurred to a greater extent. So if you look here, first very small square of size 3 by 3, it is vanished in this image. Why? Because here we are applying a mask of size 9 by 9 around this square. And here we can see that all the background pixels are very bright. And when we take average of all bright pixels with very few number of dark pixels, the average will turn out to be very bright. That's why
मैंने कल रखा था.
excuse me,
कल भी रखा था.
please,
आज भी रखा.
please mute your mics. Yash, Pranav, Nishant, please check your mics. Okay, so here in this image, these small squares are almost vanished because your mask size is greater than the square size, and overall average turns out to be a bright value. Okay, so if you look here, this first square is almost vanished, or it is appearing here with very bright level. Same is true for this second one and third one. Okay, and if you go on increasing the mask size, and if you look at the last result here, almost first 3 squares which are having very small size, those are vanished, those are replaced by pixel value which is same as background pixel value. And if you look at higher squares or squares with greater sizes, those are blurred, because here mask size is 30 by 35 by 35. So we are taking average over greater area, and that's why here blurring of these squares is clearly visible. Similarly, these vertical lines, as you go on increasing the mask size, more and more amount of blurring is observed at these vertical lines. Okay. If you compare this region with this region, large amount of blurring has occurred because of greater mask size for the last image. So with this example image, it is very clear that as you go on increasing the mask size while applying averaging filter, more and more amount of blurring takes place. Okay, so this is result of filtering by 3 by 3, and this from here all next images are having greater and greater mask size. So there is one question. This case is applicable only for averaging filter. Yes, Sharon, we are presently talking about averaging types of filters or smoothing filter. Same is true also for weighted average filter, because weighted average is also a type of smoothing filter. Okay, blurring will go on increasing as you go on increasing the mask size. But if you compare weighted average with standard averaging filter, amount of blurring with weighted average is slightly less than that for standard averaging filter. Okay, so to understand this, we are going to have a look at one more example. Okay, so for standard averaging filter as well as for weighted average filter, as the mask size increases, amount of blurring increases. Okay. Okay, now let us have a comparison between mean filter or standard averaging filter and weighted average filter. So as we studied in yesterday's lecture, here this first image gives you mask coefficients or filter coefficients for standard averaging filter, and second image indicates you filter for weighted average. Okay, so it has central pixel has highest weightage, and as you move away from the center, filter coefficient values or weight values are reducing. Okay, so at horizontal, vertical and horizontal neighbors, weight values are 2 by 16. For diagonal neighbors, weight values are 1 by 16. So this is your weighted average filter, and this is mean filter or standard averaging filter, where all weight values are identical to each other. Okay, now with one numerical, we can compare effect of blurring caused by mean filter and weighted average filter. Okay, so let us consider this input image and say we are applying both these filters on this image. Now, before going to apply actually a filter, let us understand what this image represents. Okay, so this is simple 5 by 5 image. Here you can observe that first two columns are having value 10, and rest three columns, they are having pixel value as 210. Okay, so if you visualize this as an image, between this second and third column, you will observe an edge, or there is step transition. If you look at the profile, here pixel value is varying from 10 to 210 when you move from second column to third column. So there is abrupt transition in pixel value, and it is reflected as an edge when you observe it as an image. Okay, so this basically this image represents an image with edge between second and third column. There is abrupt transition from gray value 10 to 210 when we move from column second to column third, column 3. Okay. So there is an abrupt transition. Now let us see how this abrupt transition is affected by our filtering operations, mean filter or standard averaging filter and weighted average filter. Okay, so I request all of you to determine new value of this pixel, which is indicated here in green. Now let us consider 3 by 3 neighborhood and apply averaging filter over this neighborhood in order to determine new value of this pixel with value 10. And please type your answer in the chat box. Okay, so whenever we are applying standard averaging filter or mean filter, we simply add all these pixel values and we divide it by total number of pixels. So total there are 9 pixels. So we add all these values under the 3 by 3 neighborhood indicated here in yellow color and we divide it by 9. So the resultant value is 77. Yes, I got few correct answers. Very good. Okay. So answer is 77. Now now just apply this filter on next consecutive pixel having value 210. So consider this 3 by 3 local neighborhood and again apply standard averaging filter on this particular pixel, which is indicated here green in green. So simply add all these 9 pixels, okay, and divide it by 9. So you're getting result as 143, which is average of this yellow region from the given image. Okay. Now, if we assume that the same image, same pixel values are available outside the image for say almost infinite size or very large size, we will get similar values in this column and this column. So when we apply spatial filtering, we can say that here, if you can also verify it numerically, you will get new value. This column with value 10 is replaced by values 77 and column with values 210 is now replaced by 143. Okay. So if we look at the original image, difference between these two consecutive pixels is 200, right? 210 minus 10, difference is 200. And if we look at the filtered image, how much is the difference? 143 minus 77. So difference between these two consecutive pixels is 66. So in original image, their difference was greater, right? So that greater the difference, it indicates more sharpness. Okay. Greater the difference means more is the sharpness. Now, because of application of averaging filter, this sharpness is reduced because difference between these two consecutive pixels is reduced. And that is nothing but blurring. When we visualize it as an image, it gives us blurring effect. Okay. So for these two consecutive pixels, difference is reduced. So we can say that edge from the original image is now blurred because of application of averaging filter. This difference is reduced, means it indicates blurring effect. Okay. Now let us see how much blurring is caused by weighted average filter. Okay. So simply apply weighted average filter for this first pixel and second pixel and give me your answers in the chat box. Okay, so now instead of standard averaging filter, now we are applying weighted average filter. So for weighted average filter, weight for central pixel is 4 by 16. At vertical and horizontal positions, neighbors weight value is 2 by 16 and for diagonal neighbors weight value is 1 by 16. Okay, so you will get this equation to determine new value of the pixel by applying weighted average filter. So multiply every pixel value with respective weight value and then add all these values. Okay, so result is 960 by 16. So you will get value at 60. Okay, so the same value is repeated in this column. Okay, Mahek, Soumya, your results are correct. Okay, now similarly determine new value of this second pixel by applying weighted average filter. Okay, so apply now this weighted average filter for this pixel with value 210 from third column. Okay, so when you multiply all these pixels with respective weight values, you are getting result as 2560 by 16. So it is 160. Okay. So your second column for the enhanced image or weighted average filtered image has value 60 for all the pixels, and third column has value 160. Now just compare these results with the results obtained by standard averaging filter and tell me blurring effect, comparative blurring effect. Now, if you compare these results with standard averaging filter, see this was your original image where difference between second and third column was 200. By standard averaging filter or mean filter, these are the resultant values, and for by weighted average, these are the resultant values. So by looking at these results, we can easily say that blurring effect caused by standard averaging filter is greater than that by weighted average filter. Do you agree to this statement? Weighted average filter causes less amount of blurring than your standard averaging filter, because with weighted average this resultant difference we are getting is 100 and the difference by mean filter is 66. Okay, so here difference is greater for weighted average, means there is less amount of blurring, or sharpness is more as compared to this result. We are comparing it with result of standard averaging filter. Okay, so as compared to standard averaging filter, in case of weighted average filter, blurring effect is less. Okay, hope this concept of blurring is clear to you, and comparison of mean filter and weighted average filter is clear to you. So basically when we apply blurring, when we apply averaging filters, of course edges are blurred. This is actually undesired. If you have edges or various details in the image, and if you want to preserve those details, that is not possible with standard averaging filter. Standard averaging filter causes small amount of, it causes blurring to the existing edges, but with weighted average this blurring can be reduced and edges can be preserved. Okay, so in order to remove noise even in presence of high details, it is better to use weighted average filter than standard averaging filter. Okay, both these filters are useful for removing noise, but with weighted average we can preserve the edges. Okay, or we can preserve the details as compared to standard averaging filter. Okay, now let us have a look at one more type of spatial filter. This is under non-linear filtering category, because we are not applying any linear relationship between filter and pixel values. That's why it is under non-linear filtering. Okay, so this this name of this filter is median filter. And as the name indicates, in this type of filter, we replace the pixel under consideration by median of the pixel values under the neighborhood. Okay. So all of you know that what is median? Median is nothing but central value of the pixel. So the median M of a set of values is such that half the values in the set are less than or equal to M, and half are greater or equal to M. Okay. So median represents central value of a sorted array. If we sort the given array either in ascending order or descending order, then the central value represents median value. So the same operation we are using in median filtering. Okay. So what is important about median filter is that in case of median filter, we try to replace the original pixel value by neighboring pixel values, or we try to make the pixel more like its neighbors. Okay. So in case of median filtering, new value is always an element of the original set of values. Okay. And here, in order to perform this median operation, we need sorting techniques. And all of you know that in order to sort n numbers, you need n into log of n computations. So for median filtering, number of computations is proportional to n log of n, where n is total numbers to be sorted. Okay. So if you have, again, consider this image of size 5 by 5. Now let us see how we can apply median filter to this image. Again, consider neighborhood of size 3 by 3. Okay, so this yellow square indicates your 3 by 3 neighborhood. Okay, now with the total there are 9 pixels. Now applying median filter means we need to sort these 9 pixels. Okay, so as shown here, we can arrange these 9 pixels in say ascending order as shown here. So your first pixel value is 0. Then there are pixels with value 10. Next 7 pixels with value 10. And last pixel is with value 12, which is highest value. Okay. So we consider this 3 by 3 neighborhood. We arrange these pixels in ascending order, and then we select the central value of this sorted array as median value. So for this very first 3 by 3 portion, median value is 10. And now we can replace this pixel with value 0 by median value, which is 10. Okay. Now similarly, try to find pixel new value for next neighborhood. Simply scroll this mask by one column, go to next position and determine new value of this particular pixel. Okay, so you will get new 3 by 3 neighborhood. Arrange these numbers in ascending order and tell me what is median value. Okay, or filtered value. Okay, Sakshi, I request all of you to type your answers. Just you have to determine median of these new 9 pixels. Yes, Mahek, Soumya, Sakshi, your answers are correct. Okay, so we can, this is your new neighborhood. Arrange these pixels in ascending order as shown here. So 0, then 9, then 10, 10, 10, 5 times, then 11 and 12. And this central value is again 10. So this new pixel value is 10. Okay. Now you can go for next pixel. 3 by 3 neighborhood for next pixel. Arrange the pixels in ascending order and determine new value of pixel, and similar process you can apply for second row as well as third row. Okay. So this is your third pixel value of enhanced image or median filtered image. And similarly, you can determine new values for next 3 pixels from second row. And similarly, you can determine new values for 3 pixels from the last row. Now just do it, this last one. Okay, here this is your neighborhood and determine new value of the pixel 255 with value 255. Okay, directly go for last pixel and tell me its new value. Okay, I'm getting few answers from Sakshi, Sai, Pranav, Sanidhya. Very good. Shravan, I'm getting answers. Very good. Okay. So if you arrange these 9 pixels, you will get this as sorted array, and this central value is 11. So new value for this pixel is 11. Okay. Now I purposely selected this image. In this image, there is a pixel with value 0 at location here. And at this location, there is a pixel with value 255. So this 255 represents high intensity spike and 0 represents low intensity spike. Okay. So this is nothing but your image is corrupted by salt pepper noise. And if you observe result of applying median filter, we can say that this salt pepper noise is removed because of application of median filter. Right? Do you agree to this statement? This high intensity spike as well as low intensity spike, these are removed because of application of median filter on the image. Because if you look at the result, your 0 is replaced by 10. Even this high intensity spike 255 is replaced by 11. So we can say that median filter is very useful to remove salt pepper noise from the given image, right? Now, instead of median filter for this same location, if you apply standard averaging filter, tell me what is resultant value. What is new value of this original pixel with value 255? Instead of median filter, now apply standard averaging filter and tell me new value of this particular pixel. By standard averaging filter or mean filter, just tell me what is new value of this pixel. Yes, Shravan, your answer is correct. Yes, Pranav, your answer is correct. So, yes, Sharan, very good. All of you are giving me correct answers. Okay, so in case of standard averaging, we take simply average of all these pixel values. So it will become 255 plus 87 divided by 9. So the result is approximately 38. Okay, so with standard averaging filter, this 255 or high intensity spike is reduced to a value 38. And if we compare it with result by median filter, this value is reduced to 11. So median filter is more effective in removing high intensity spikes and low intensity spikes than your standard averaging filter. Of course, standard averaging filter it has reduced that salt pepper noise to very great extent. Okay, but it is not as close as neighboring pixels. Still, it is different than neighboring pixels, or it is greater than neighboring pixels. Okay, so by standard averaging filter, we can say that salt pepper noise is not reduced uh, to large extent. Okay, still there is some noise. Only its intensity is reduced. Okay, because this 255 high intensity spike 255 is now converted to level 338, which is much less than 255, but the noise is not removed completely. Okay. So we can say that median filter is effective than mean filter in removing salt pepper noise. So hope this comparison between median filter and mean filter is clear to all of you. And you can also observe this comparison uh, with actual images. This is a PCB image which is corrupted by salt pepper noise. You can observe many high intensity and low intensity dots on this image. This is nothing but salt pepper noise. This is result of filtering this image by using standard averaging filter or mean filter, and this is result of filtering this image by median filter. So we can easily understand that with median filter, salt pepper noise is removed to very high extent. It is almost nil in this result, whereas by uh, mean filter, it is not removed to large extent. Even by applying mean filter, these dark and white spots, those are blurred, but those are not removed completely by your standard mean filter. Okay. So this is a summary of all smoothing filters that we have studied. So we have studied mean filter, that is standard averaging filter. It is also known as box filter. And this mean filter or arithmetic mean filter is useful to remove white noise or zero mean noise. Then we also studied weighted average filter. This weighted average filter is useful to filter images with very high details, because whenever there are very high details, we need to preserve those details. So in order to preserve the high details, we can go for weighted average filter. And this weighted average filter is very useful to remove noise with which is with Gaussian distribution. Okay. And it is useful for filtering high detail images. Then third type we have studied is median filter. It is useful for removing salt pepper noise. Okay. So like median filter, there are few other examples of non-linear filters known as mode filter, maximum filter, and minimum filter. This mean it's MIN and it is not MEAN mean filter. This MIN mean stands for minimum filter. Okay, so let us have a quick look at mode filter, max filter, and mean filter. So mode represents most frequent pixel value. So if we consider this 3 by 3 neighborhood, again, like we did in median filter, we can arrange these filters. Uh, we can arrange these pixels in ascending order, and we can check which is the most frequently occurring value. So here we can see that most occurring pixel value is 11, and this represents mode value of the given array. Okay, so for this 3 by 3 neighborhood, we replace this pixel with value 20 by its mode value, that is 11, mode value of the neighborhood. Okay, so this is meaning of mode. Okay, so here by mode filtering, we are actually replacing pixel under consideration by mode value of the neighborhood. Okay, then maximum filter. So as the name indicates, we are replacing the pixel under consideration by maximum value in the neighborhood. Okay, so for this particular neighborhood, 3 by 3 neighborhood, we can again sort the array, and this value indicates maximum value. So maximum value is 20. So the filtered value is same as original for this particular example. Okay, this maximum value is same as original. So new value is 20 for this particular example. Now consider this particular neighborhood, okay, and tell me new value of this pixel with value 10 by applying maximum filter on this neighborhood, 3 by 3 neighborhood. What is new value by maximum filter? Yes, Sharan, your answer is correct. So if we apply maximum filter for this 3 by 3 neighborhood, again maximum value is 20 and you will get for this particular portion 3 by 3. If you arrange these values, maximum value is 20. So you need to replace this value by 20. Yes, Keshav, Sai, your answers are correct. Now the third type of last type of non-linear filter, that is minimum filter. So as the name indicates, we replace this replace this pixel value by minimum of the neighborhood. So again consider this 3 by 3 neighborhood, arrange these pixels and replace pixel under consideration by this minimum value, which is 10 in this case. Now, answer my question. Say, if we have an image which is corrupted by high intensity spikes, which filter of the two filters is useful? Minimum filter or maximum filter? If we are having an image which is corrupted simply by salt noise or high intensity spikes. Yes, Sai, your answer is correct. If we want to remove a noise which is of type salt noise or high intensity spike, you have to use minimum filter. Very good. All of you have answered correctly. Mehak, Pranav, Sharan, Keshav. Very good. Similarly, if I have an image which is corrupted by paper noise or which is corrupted by low intensity spikes, whether you will go for minimum filter or maximum filter. Okay, very good, Sharan, Keshav, Mahek. We need maximum filter to remove those low intensity spikes. Okay. And if your image is corrupted by salt pepper noise, you can go for median filter, because median filter makes your uh, pixel more like its neighbor. Very good, Soumya. All of you have answered me correctly. Then let us have one more few additional variations of smoothing filter. Basically, whenever we know that our image, input image, has lots of edges and it is corrupted by noise. Now, in order to remove noise, we have to apply some smoothing filter. Okay, but side effect of applying averaging filters is that it gives you blurring. It causes blurring of those edges. So in order, if you have lots of edges or details in your image, and still if you want to remove noise because your image is corrupted by noise, then you can go for directional smoothing. Instead of using standard averaging filter or weighted averaging filter, you can use directional smoothing. Let us see how it works. So as shown here, in case of directional smoothing, it determines average in these four directions and it selects that average value which gives you minimum average. Okay, so here, or it gives you average. You can, out of these four averages, you can select that average which is closest to the pixel under consideration. Okay, so you have to check difference between the average values and pixel under consideration and select that average value out of the four values, which gives you minimum difference with respect to the pixel under consideration. Okay, so this is meaning of directional smoothing. This directional smoothing is also known as selective smoothing because we are applying averaging selectively over possible direction, and it also comes under anisotropic filtering. Why? Because anisotropic filtering has effect of smoothing which is not same in all directions. Okay, so it is not isotropic, that's why it is also known as anisotropic filtering. Okay, so in case of directional smoothing, as shown in this particular example, we take average over vertical direction, then diagonal direction plus 45, then we take average along horizontal direction, and then say along diagonal, that is minus 45 degrees. Okay, then we will get, so average of these three pixel values, 10 plus 10 plus 10 divided by 3, it gives you average value as 10. Similarly, in this direction, you can determine average of these three pixel values, 220 divided by 3. Then you can determine average in this direction, say it is D3, and in this direction, say it is D4. Then compare these four average values, D1, D2, D3, D4, with your central pixel value, that is your pixel under consideration. And out of these four values, select the one which gives minimum difference with respect to central pixel value. Okay, so for this current example, closest to central value is D1. So we select this new value of the pixel as D1. Okay, D1 is 10 and D2, D3, D4 are greater than 10. So difference with respect to pixel, current pixel value is greater. Okay, so this is directional smoothing. Then let us have a look at one more variation under selective smoothing known as conservative smoothing. Okay, so in conservative smoothing, we again try to make the pixel under consideration which is similar to its neighbor. Okay, so here this is the algorithm. We compare, so for a center pixel, find the pixel values of its 8 neighbors. Okay, so in this case, we can simply consider 8 neighbors. Okay, and we, for those 8 neighbors, we determine minimum value and maximum value, and we compare this central pixel with minimum value of the 8 neighbors, and we compare this central pixel with maximum value of the 8 neighbors. Okay, now if this central pixel is in the range between minimum to maximum of the neighborhood, we retain this pixel value. And if this central pixel value is greater than maximum value, we replace it by maximum of the neighborhood. If this central pixel value is less than the minimum value, we replace the pixel under consideration by minimum value of the neighborhood. Okay, and if it is within the range, we retain that value. Okay, so this is conservative smoothing. So this conservative smoothing has similar effect to median filtering because we try to make the pixel more like its neighbors. Okay, we replace it by one of the values from neighbors if it is outside the range between minimum and maximum of the 8 neighboring pixels. Okay, so this is another type of selective smoothing known as conservative filtering. Okay, so here one example of conservative filtering is shown. So this is your original image. This is image corrupted by Gaussian noise. Okay, so your original image is corrupted by Gaussian noise. And then if we apply conservative filtering, we are getting this result. So this Gaussian noise is reduced to large extent because of conservative filtering. Okay, so this is algorithm for conservative filtering. If your pixel under consideration is in the range minimum to maximum of 8 neighbors, we retain the pixel value. If pixel value is greater than maximum, we replace it by maximum of the neighbors, 8 neighbors. And if pixel value is less than minimum value, we replace it by minimum value of the 8 neighbors. Okay. So hope these small variations of smoothing filters are clear to you. Okay. Now let us go to next topic, that is spatial filtering known as sharpening filters. Okay. So edge detection is one of the type of sharpening filters. Okay. So we can use these sharpening filters as a pre-processing technique. Whenever we are going for image analysis, we need to detect object boundaries. Okay. So in order to detect those object boundaries, we need pre-processing step, that is sharpening those edges. Okay. So main intention of these high pass filters or sharpening filters is to sharpen the image. We can use it as pre-processing step of image analysis applications. Okay. So in order to understand sharpening filters, we need to know about basic mathematical operations, that is differentiation. Because in order to sharpen the image or in order to apply high pass filter on the image, we need this basic mathematical operation, that is derivative. All of all of us are familiar with integration operation. Integration operation is equivalent to low pass filtering, and similarly differentiation operation or derivative operation is similar to, it is analogous to high pass filtering. Okay. So let us have a look at how we can determine derivative of the given image. Okay. So before going for image, well, let us determine derivative of one dimensional data. So if we consider profile of any of the rows from the image, that gives us one dimensional data, right? Now this particular is profile of a line which is passing through this dot. Okay. There is a bright white dot, and if we consider that particular row from the image, and if we vary column numbers, we get this profile, right? Here initially in this row there are very bright pixels. This brightness is reducing slowly, so it is indicated here by this region of the profile. Then there are few dark pixels. So those are represented here. These are dark pixels. Then there is sudden transition from dark to brightest level, white spot. Okay, so it is indicated here. Then next few pixels, they have zero value or black value. So it is indicated here. Then there is a slant line which has brighter gray shade. So this slant line is shown here with this particular portion of the profile. Again, there are few black pixels. Those are indicated here. And after black pixels, there is sudden transition from dark to bright level. And it is indicated here by this portion in the profile. Okay, so this is step transition. Okay, so let us see how we can determine derivative of this particular profile. Okay, so to make it further simpler, what we are doing, we are, instead of considering all columns, we are considering few samples on x-axis. So we are considering few columns, and similarly, instead of considering 0 to 255, we have quantized y-axis to 0 to 7. Okay, so this particular profile is quantized and sampled version of this profile. Okay, so this is your profile. Now how we determine first derivative? So the same profile is displayed here as numbers. Okay, so first two pixels are having value 5, 5. Then there are few pixels with value 4, 3, 2, 1, 0. Then few pixels with 0 value. Then there is isolated point, which is 6. Okay, again few pixels with value 0. Then there is this thin line, which is shown here with pixel values 131. Then again, there are dark pixels with value 0. Then there is sudden transition from 0 to 7. Okay. Now, in order to determine first derivative of this pixel, what operation we use? It is simple difference operation, first difference. Okay. So we consider consecutive difference between consecutive pixels. Okay, so 5 minus 5 is 0, 4 minus 5 is minus 1, 3 minus 4 is minus 1. So you will get these difference values. Okay, are you able to see these difference values? This is first derivative, difference between two consecutive pixel values. Okay, so this is your first derivative. Now, how we determine second derivative? Second derivative is simply difference of difference. So if we take difference of these first derivative values for two consecutive values, we get second derivative. So here, these are the second derivative values. Here, no value is available. So it is considered as 0. 0 minus 1 gives you minus 1. Minus 1 minus 1 minus 1 minus 1 gives you 0. Then next, all pixels have same value. So you are getting 0 derivative here. Then here, derivative value is 1. 0 minus minus 1 gives you 1. Then 0 minus 0, 0. 6 minus 0 gives you 6. Minus 6 minus 6 gives you minus 12, and so on. So this is how you can determine second derivative. Now looking at these first derivative and second derivative values, we have to conclude something. These conclusions are very important. Okay, now if you look at the ramp portion from the given image, this ramp indicates thick line in the image. Okay, so this is ramp portion equivalent to this region. You are getting ramp portion. So this is thick line. Okay, this is your thin line and this is thick line. Okay, so this ramp indicates thick line, and along the ramp portion you are getting second derivative value at 0 and first derivative value is minus 1. Okay, so we can say that first derivative is more useful to detect thick lines. For second derivative, we are getting 0 value because along the ramp, slope is constant. Okay, so that's why you are getting 0 value. So first order derivative is generally useful for producing thick edges or for enhancing thick edges. First order derivative is useful. Now, if you look at the isolated point or thin line, along isolated point, second order derivative amplitude is greater. Simply consider the difference value. It is 12 here and it is 6. Similarly, for thin line, second derivative value is 4, and that's for first derivative is 2. So we can say that second order derivative is very useful to detect isolated points and thin lines, or to enhance fine details in an image. Second order derivative is better than first derivative. Okay, and if you look at the step change, again at step change, first order derivative gives you strong response. So for thick lines and step changes, we can use first order derivative, and for isolated points and thin lines, we can use second derivative operation. Now I request you all to type your attendance. Okay, first, last 5 digits of your PRN number followed by your name. And if you have any doubt related to these uh, sharpening filters, please ask your doubt. If no doubt, you can leave the meeting.